Almost every building, from residential to commercial skyscrapers, requires HVAC systems to operate autonomously, from controlling the air temperature to ensuring the air is safe to breathe. So, how do engineers achieve this? That's what we'll be covering in this video, which is sponsored by Danfoss. They have a series of high-quality, on-off, modulating and digital actuators for control valves in all HVAC applications, and I recommend you go and check them out. Danfoss have put together an easy-to-use interactive infographic to help you match their popular ABQM pressure-independent control valves to actuators. I'll leave a link for you in the video description down below. We rely on our heating and cooling systems to function whenever needed, especially on the coldest and hottest days of the year when the system must operate at full capacity. To achieve this, the systems are typically oversized, so that they can handle the worst-case weather scenario. However, most of the time the system will operate well below this point at part load conditions. The heating and cooling loads change throughout the day and also the year due to variables such as solar heat loads, building occupancy, ambient temperature, equipment, etc. The HVAC system needs to react to these changes to maintain comfortable and safe conditions for people, animals, food and products, equipment, etc. The system consists of many components. As one component reacts to a change, it will often impact another part of the system. So, we need controls to automatically sense a change and act upon this. There are many types of controls, as well as methods of controlling systems and components in our HVAC systems. These will range in complexity, and we will go through the basics of these now. But first, I want you to tell me in the comment section where you have seen the different controls used and what for, or what ideas you have for where to use them. The simplest form of control is an on-off switch. For example, to control the heat output from an electrical heater, we can manually switch it on or off. We could automate this, for example, with a bimetallic strip which acts as a thermostat. The strip bends as it warms up, and at a certain temperature, it will bend enough to disconnect the circuit and turn the heater off. As it cools down, it completes the circuit again, and the heating turns on automatically. We usually connect a manual switch with a thermostat so that a user can override the heating if they are too hot. We could also control a heating or cooling system with a simple on-off control. For example, if the heating or cooling demand for a room is only half of what the system can provide, then we could just turn the system on for half of the time and off for the other half of the time, perhaps every 30 minutes. This would work, but not very well, because it results in the room being too hot and then too cold, although the average temperature appears normal. To improve this, we could divide this into smaller time intervals, which would achieve a more even temperature. Time control allows systems and components to turn on and off at certain times, as well as for certain durations of time, or we can delay something turning on or off for a certain amount of time. For example, on a cold morning, we want the heating to turn on before we wake up, so that the house is nice and warm. A simple time control uses a cam to push contacts together and complete a circuit. As the time dial rotates, it will force the cam to open and close the contacts to turn the heating on and off. Timers used to all be mechanical. However, these days timers are usually electronic and typically use relays to open and close circuits. By the way, we have covered how relays work in detail previously. I'll leave a link for you in the video description down below. Electronic controllers are compact and much easier to use. They have far more functions, but usually at least a 7-day time schedule with multiple on-off times per day. This is useful, for example, in a small office, which is closed on weekends. So during the winter, the heating is scheduled to turn off on weekends, and then it starts slightly earlier on a Monday morning because it will take longer to warm the building up. A more sophisticated system, typically used in much larger buildings, will use an optimizer. And for this example, we have it connected to a programmable logic controller. This will check with the clock, should the heating turn on today? And if so, at what time will the building be occupied? The clock replies yes. The scheduled occupancy time is 9 a.m. The PLC checks the current temperature of the room and calculates the difference between this temperature and the desired temperature. It then checks the outdoor temperature to calculate how long it will take to heat the building, because on a cold day it will take longer, so it will need to start earlier. Turning systems or components on and off to regulate the room temperature does work, but not very well. Instead, we can modulate the thermal output by increasing and decreasing the temperature to match the actual load. For example, in this simple heating system, we have a thermostat in the room to measure the temperature, and then a controller will compare this to the desired set point temperature and decide if the room is too hot, too cold, or just right. If it is too cold or too hot, then the controller alters the position of the motorized valve to increase or decrease the amount of hot water entering the radiator. We have two main types of sensors, digital and analog. Digital inputs can only tell if something is on or off, nothing in between. For example, an on-off switch or a bimetallic strip. The circuit is either open or closed. So we can only tell if the temperature is above or below a certain temperature. Analog inputs vary their signal. They might vary in resistance, voltage, or current between a minimum and maximum value. So we can use these to determine the exact temperature or pressure. We have covered how temperature sensors work previously, and I'll leave a link for you in the video description down below. The thermostat could be located on the output device, like a thermostatic radiator valve, or remotely, like a room thermostat, which controls the position of a damper in a fan coil unit. To alleviate swings in temperature, we set a dead band condition, typically plus or minus 1 degree Celsius from the required temperature. For example, if we want a room temperature of 21 degrees Celsius with a dead band of plus or minus 1 degree, the heating will turn on when the room temperature falls below 20 degrees Celsius, and it will then switch off when it is above 22 degrees Celsius. This gives us an average temperature of 21 degrees Celsius. The deadband values depend on many factors. It can be modeled on a computer, but generally it is found through trial and error, with small incremental changes to find the optimal point where the room is comfortable and the system operates efficiently. On and off control makes it difficult to maintain a desired temperature. Instead, we can use special valves to modulate the thermal output, keeping the temperature within a certain deadband. In a simple heating system, when the gas boiler turns on, it will run at full power to heat the water, but then it reduces the gas supply by using a motorized valve. This reduces the heat output of the boiler. It does this instead of turning it off. The water temperature set point is kept in the dead band, so the heat output is equal to the heat leaking out of the room. Most systems have a single heating or cooling source with multiple radiators or fan coil units connected to this. These are usually in different rooms, so we need to control the output of the individual units. The simplest method to achieve this is the thermostatic radiator valve. This is a valve found on heated water systems. It basically uses a chamber filled with a wax, liquid, or gas, which expands and contracts as the room temperature changes. This controls the valve position. The hotter it gets, the further it closes the valve. The colder it gets, the more it opens the valve. The heat output of the radiator therefore matches the demand of the room. Alternatively, a radiator or fan coil unit could use a motorized valve, which is controlled by a thermostat in the room. This will vary the flow rate of hot or cold water into the unit. This will vary the thermal output of the unit to match the demand. However, if a fixed speed pump supplies multiple units, then as one valve closes, it causes a pressure increase in the pipework, so the flow rate of water increases through the other valves. That's a problem because it will increase the heat output. The valves will constantly adjust to try and maintain the correct temperature. We will therefore lose control of the system, and as the valves are working so much, they will break down much faster. To overcome this, we could install a pressure sensor and a variable speed pump. As the valve opens and closes, the pump changes speed to try and maintain a constant pressure and thus a constant flow rate through the radiators. This happens regardless of when another valve opens or closes. We have covered how variable speed drives work and also how pumps work in our previous videos. Do check those out, I'll leave a link for you in the video description down below. Alternatively, we could use pressure-independent control valves. As the name suggests, these valves maintain a constant flow rate through the valve, independent of the pressure fluctuations in the system. These are used in heating systems, but also, for example, in a central cooling system in a commercial building, to control the flow rate through the fan coil units. These will be used to control the flow rate through fan coil units, air handling units, etc. These are basically multiple valves combined into one design. The lower part maintains a constant pressure difference across the valve, and the upper part regulates the flow rate. We have covered how pressure-independent control valves work in detail previously, and I'll leave a link for you in the video description down below. We also need to regulate the quality of air. For example, in an underground car park, we might find a carbon dioxide sensor which controls the speed of the ventilation. Rather than running the fans constantly at high speed when they're not needed, the fans vary their speed to match the ventilation required, depending on how much carbon dioxide is in the air. Check out one of the videos on screen now to continue learning HVAC engineering, as this is the end of this video. Don't forget to follow us on Facebook, LinkedIn, Twitter, Instagram, TikTok, as well as theengineeringmindset.com.